So no specific questions? The what? Yeah, sure. What are you talking about? Which one was it? The chain rule? Oh. Was it extra credit?
I don't know. This is a take-home quiz.
Take-home quiz. Okay, yeah, turn it. Way to go, Sophia. Yeah, so you can turn it in, or you can turn it in next time, but you won't get full credit for it. But if you have it now, turn it in. Probably over here. That's good. That was what, number 52? Out of the book? See, I would have known. I looked right here. I have it written right here. Find the equation of a tangent line to a curve. Is that the one? Okay. All right. Yeah, square root of 3 plus x squared. So y'all don't have to blame it on Sophia. I would have looked at my notes right here and seen it. Still, though. Okay, thank you. Okay, so I'm a little concerned that you don't have questions over chain rule. That you all did your homework and everything went great. That's a little concerning. How about we try a few and see how it goes? Let me just make one up. How about this one? Y equals, in parentheses, x squared plus x plus 1 over x squared minus x minus 1 all to the 5th power. So what we're going to do here is try and find y prime, find the derivative. All right, so when you look at this, what are you seeing? You see some chain rule? Explain. You see the 5th power. So the way you can look at this, remember, chain rule, what you're trying to do is look at it almost like an onion. You have like an inner layer and then this outer layers, which are the outer functions. And so one thing you can do is imagine if you were to plug x in right now, like if I gave you a value of x, what would you do first? Well, you would plug x in here and here, right? And then you'd figure out what that quotient is. And then after you're done with that, you'd raise it to the 5th power. Agreed? So now when you're trying to figure out what rule to use here for differentiation, you can say, well, what was the last thing I did? The last thing that I did was the 5th power, right? So ultimately, the outer layer of this is something that's raised to the 5th power. So it looks like, almost like x to the 5th. How would we take the derivative of x to the 5th? We just drop the 5 down, reduce the power by 1, right? So the outside function here is the 5th power. So we know we're going to need to bring the 5 down, reduce the power from 5 down to 4, but then we have to go inside here and take the derivative, right? That's what the chain rule says. So now what we're going to have to look at is in here, what do we have? A quotient. So we're going to have to tack on to the end of the chain rule, we're going to have to tack this quotient on, the quotient rule. Does that kind of make sense? Okay, so let's go for this. Let's see if we can get this first part. Y prime will be, we said, the 5. And then what goes in the parentheses? All of that stuff, right? This stuff, but I'm not touching it. I'm just going to leave it alone. So I've got x squared plus x plus 1 over x squared minus x minus 1. All of this raised to the 4th power, right? So this was like what I was doing in class before, where I was like, okay, we have like this cloth raised to the 5th power. The derivative of this cloth to the 5th power is 5 times the cloth to the 4th power, right? We all good? Okay, now, what comes next? Multiply, right? Because chain rule says multiply now by the derivative of the inside. We need to now take the derivative of this, right? And to do that, we're going to need to use the quotient rule. Now the quotient rule, just as a reminder, is f prime g minus g prime f all over g squared. You should have that memorized by now. F here represents the numerator function, and g represents the denominator function. So if I were to write this out, I'm going to go f prime g minus g prime f all over g squared. So we'll take it slow. I'm going to take f prime, so I'm going to take x squared plus x plus 1. I'm going to take its derivative, right? I haven't done that yet. Times g, which is x squared minus x minus 1. Then minus g prime, which is x squared minus x minus 1, that derivative. And then times f, which is x squared plus x plus 1. I'm trying to squeeze this on camera, but x squared minus x minus 1 squared. So does everyone see this formula? Do y'all see the formula? Okay. I have not taken these derivatives. All right. I noticed on a few of your quizzes that a few of you were doing it like this, which is fine. Okay. So I wanted to show it that way also up here. Okay. So now I'm just going to rewrite 5 x squared plus x plus 1 all over x squared minus x minus 1, all of this to the 4th power times. Now let's go ahead and do these derivatives. So what is the derivative right here? 2x plus 1, right? The derivative of that 1 goes to 0. So we just get 2x plus 1, got to put it in parentheses, multiplied by x squared minus x minus 1, then minus, now the derivative of this, which is 2x minus 1, and then times this piece, which is x squared plus x plus 1, and then all of it over the denominator squared. And this is our raw derivative right here, right? At this point, we have done the calculus. We've differentiated, and all is good. Yes? Questions? Now we could clean this up a little bit. The cleaning up that you could do is by expanding this out. What I mean by that is this times this, this times this, this times this, and then 1 passes through. Then over here you could do this through, and then the negative 1 through. So you would get a total of, 6 terms from this expansion. You would get 6 terms from this expansion. You would have to distribute the negative through to each one of those. Then you collect like terms, and that would be about as far as we would want to go. All right? I'm not going to do that because that's just algebra at this point. Remember, when you take your test, if I just give you a function, I ask you for its derivative, about 80%, 70% of the score is going to be just, can you get the raw derivative? Maybe 60. Well, it depends on, if I ask you for the tangent line, right? If I ask you for the equation of the tangent line, you actually don't need to simplify this, right? Because all you have to do to find the equation of the tangent line is plug a value of x into this. And so there's no need to clean it up algebraically if all you're going to do is plug a value in later. So, but if I ask you just for the derivative, I want to see you can do the calculus. Understand? The algebra is just kind of, well, I assume you can do it, but you won't lose complete credit for not doing the algebra correctly. All right. Shall we move on? Another one? Questions? Is there anything about this that you're just still like really confused on, that you just don't feel like you're getting, or come on, I need something from you. If not, we just the train keeps going. You're not going to help me, are you? Okay, all right, let's try this. Where was that one? Where was that one? Where was, oh, there it was. Oh, that's a homework problem. All right, this is straight out of the book. All right, so I'm not making this up. Yes?
Oh, just say, I guess the ones that kind of like are hard for me, the ones that need like a lot of, I guess, simplifying. It's hard for me to like just see, you know. So I think on one of the questions I wrote, like 19, like a lot of simplifying to do.
Oh, yeah. Mm-hmm. Yep. And what you want to do is just see if you can get to the answer. You know, it's a lot of algebra, but I guess that's the nature of the beast. All right, so we've got this, tangent pi x. I promised you from day one that calculus will force you to become good at algebra, or, you know, it'll cripple you, one or the other. You're either going to have to get good at algebra or you're going to struggle. All right, here we go. Okay, so let's try and think about this. If you plugged x in, like a value for x right now, it would go right here. First thing you would do is you'd multiply it times pi, right? Then you would take tangent of that. Then you would take sine of that. Then you would take the square root of that. And then you would take cosine of that, right? Right? So that looks like multiple layers of composition. There's no multiplication, there's no products in here. Well, the only product we have is right there. But that's a constant times a function, right? So we don't have any product rule. We don't have any quotient rule. All we have is chain rule here. Agreed? Okay, so let's start with the outer function first. The outer function is cosine, right? And it's cosine of everything we see here, right? Cosine of that. So what is the derivative of cosine of something? Negative sine of it, right? So I'm going to put negative sine of what, though? Of everything that I put in that blue box, right? It's the entire square root of sine of tangent of pi x. Okay. That is the derivative of the outer cosine function. Agreed? Okay, so we have done the outer cosine function, and now we can move inside and start doing the next layer. So what was the next layer? The square root was next. And we have the square root of sine tangent. So let me show that. We are now going to be working on the square root, right? This is the part we're working on now. And we're doing square root of all that junk right there. Yes? So what is the derivative of the square root of something? 1 over 2 times the square root of that something. So I'm going to say times 1 over 2 times the square root of whatever that something is. And that something for us is sine of tangent of pi x. Sine of tangent of pi x. So that just goes back, if you've forgotten, hopefully you have not, that the standard formula for the derivative of square root of x is something you need to memorize. It's 1 over 2 root x. Okay? I'm using that to get this. I'm not done, right? I have only gone through and done the cosine, and I've done the square root. What's the next layer in? Sine, right? Sine of this, right? So if I'm going to take sine of something and take the derivative, what is its derivative? Cosine. So I'm trying now to take the derivative of sine of this junk right there. So what is, you said that would be multiplication again, right? And derivative of sine you said was cosine. And inside of that goes the red box, tangent pi x. I'm going to run out of room here. Still going, all right? Still going, because all we've done now is taken the derivative of sine. So now we go inside and take the derivative of tangent of pi x. So what is the derivative of tangent of something? Secant squared, right? Of that something. Now, notice that the pi x in here is a linear expression. And we talked about this last class, that when you had like sine of ax plus b, that when you took the derivative, you'd always get the a to pop out. Well, we have tangent of pi x. Pi x is linear, so that a is going to pop out. So the pi is going to pop out, isn't it? So I have added on to this, but I'm going to go down here so it's on camera. I have times secant squared of what, though? Secant squared of pi x. And then here comes the pi that pops out, times pi. And I've done the tangent, and obviously I did, well, is it obvious? I did the derivative of pi x. That's where the pi came from at the end. Okay, so we're done. We've gone from the outside all the way in. And there's not a whole lot of simplification you can do here. I mean, there's not, you know, we can't like multiply things out, like expand or anything, because everything's multiplied together already. The most I would probably say you could do is rewrite this where you have this, this, and this all together in a numerator over this. That would be about as clean as you could go. And then you can move like the pi out to the very front next to the negative, like negative pi and then all that. All right, so that problem was in the book. All right, so it's just so you know I'm not like trying to come up with crazy hard problems. This is the level that they believe you should be at for this. Do you feel like I've given you enough examples, or do you want more? What do you feel like? Well, I think I heard more. Did I hear more? Yes? Okay. Let me give you another one. How about this one? Y is equal to... I wonder how easy this would be. Give me just a second here. Whoa, what is that? Here we go. Oh, we haven't done natural log. Shit. I was trying to give you something from an old exam, but all of these have stuff we haven't talked about. Okay. Here's what I was thinking. How about secant of x squared sine x. Find the derivative of this. Okay, so we're trying to again come to grips with what's, you know, how we do things in terms of the order in which we do things. So if we were x, what would happen? If you plugged an x in, you'd go here square, right? And it would also go into the sign at the same time. And you get those two results and do what with them? Multiply them together, right? So we do have a product here, don't we? We have a product in there. But then after we do that, we would take secant of it. So the outside last thing happening is secant, yes? So that means if we want to take derivative of this, we have to start out with the chain rule, starting with the derivative of secant. Okay, so let's try that. What is the derivative? Just as a reminder, what's the derivative of secant x? Secant x tangent x. right? And if you haven't memorized that, it's on your formula sheet, right? So this is what I'm going to use. The important thing, though, is that I don't have x, right? I have secant of all of that junk right there. So the derivative of this is going to be secant of that junk, tangent of that junk. So it's going to look weird, but that's what it's going to be. Secant of all of that junk in there times tangent of all of that junk in there. So do y'all see that that is just the derivative of the outer secant part? Okay, since this was chain rule, I now say times the derivative of what was inside. So with the inside piece, we actually have something like f times g, and the derivative of that is f prime g plus g prime f. So that's our formula for product rule. See that we have a plus sign here? That means when I take the derivative of the inside, I'm going to have two pieces separated by addition, right? Which means that all of this junk right here is going to have to multiply times both of those. Which means I need to put this answer either in brackets or parentheses. They're the same thing. Brackets and parentheses are exactly the same thing. I'll do brackets just because I really want to stress that you have to have these, okay? Because all of this junk would have to get distributed through to each one of those. Each one of the two pieces that's going to come from this. Okay, so inside, let me get my product rule ready to roll here. I know I'm going to have a plus in the middle. I'm going to have f prime g plus g prime f. So can you tell me what is f prime g? 2x times sine x. Okay, so that's your f prime g. And then plus, now your g prime f. So g prime, derivative of g is cosine x times x squared. And just remember, this x squared cannot go inside and join with this x. It has to move out in front. So the most you could probably do here is just rewrite that as x squared cosine x. This is pretty much clean. You can't really do anything with that. And you do not have to distribute this through, okay? I'm not saying that you have to, but you have to have brackets or parentheses. Do y'all understand why? You sure? Okay. That would be it. I would like to compare that answer right there. Let's do a different problem underneath this. I'm just going to tweak that problem just a little bit. I'm going to do y is equal to x squared secant of sine x. So I rewrote the problem a little bit. Instead of putting that x squared inside the secant, I actually pulled the x squared out. Now how does that change the approach? We actually have, if we plug x in, right? X goes in here. Sine of that, then secant of that, but multiplied, right? So we have multiplication here between two things. We have an f and a g, right? And it's not inside, the f times g is not inside another function. It is actually the outside, so to speak. So we have to start with the product rule. We have to take the derivative of this times this plus the derivative of this times this. Make sense? Now, is the derivative of that going to be hard? Just 2x. So we'll have 2x times this plus, now the derivative of this is going to require what? That's chain. That's composition. That's a function inside of a function. So this is a chain rule that is going to happen inside of a product rule, as opposed to this, where we had a product rule occurring inside of a chain rule. See the difference between the two? Okay, so let's do our y prime here. I'm going to write it out a little bit different. I'm going to say it's going to be f prime g plus g prime f. So I have identified that this is f and this is g, And this right here is f prime times g plus this is g prime times f. I have not taken the derivatives, right? I have not taken the derivatives. This was just to illustrate the formula in action. Questions? Everyone said they were comfortable with the derivative of x squared, right? This one right here is going to be a little bit messy. Not too much, but a little bit. So why don't we go take the derivative of this on the side somewhere? That way we can, bring it back into our answer. So I'm going to just erase this. So I'm kind of doing a problem within a problem here. I'm just going to write down secant of sine x. If you were asked to take the derivative of that, you would have to use chain rule. So you'd start with the outer function, which would be what here? Secant. So I'm trying to take the derivative of secant of something, right? The derivative of secant of something is secant of that something, tangent of that something. So what's my first little piece here? Secant of sine x, and then times, right? So times secant of, tangent of sine x. Am I done?
No.
No. Now I need to take derivative of what's in here, which is just cosine x. That is just this piece, right? That's just that right there. All right, so I think I'm ready for y prime here, down here. Y prime should be derivative of x squared, which is 2x, times secant x sine x, then plus, and now the derivative of this, which I wrote up there, right, times x squared. I'm going to put the x squared in front. X squared secant of sine x tangent of sine x and then cosine x. I think I'm going to highlight where my multiplication is real quick. Everywhere you see a blue dot, that's where I have multiplication. Just the reason I'm doing that is I want everyone to understand secant sine x, this is secant of sine x, right? This is not secant time. I mean, that doesn't make sense to say secant times sine x. It's secant of sine x. All right, that good? Okay. We could go on. We could maybe factor out. They both have some common factors, right? We're not being asked to factor. But you could see that you have a secant sine x here, a secant sine x here. You have one factor of x, right, that you could pull out of both of those. So you could factor out of both of these an x secant sine x if you wanted to, if you needed to, you could. All right. More. There's no such thing as doing too many chain rule problems. How about I'll put 2 on the board and I'll let you work and see how you do. I'll put 3. I'm going to put easy, medium, and hard, all right? And let's see. I'll put like a C level problem, a B level problem, and an A level problem on there.
So
all right?
is A the hardest or C the hardest?
A. Yes. All right. So the first one, y equals, let's go with square root of tangent x. I'm thinking chain rule here, okay? Next problem, y equals square root of x tangent x. These are all going to be looking pretty similar to one another, all right? And the last one will be, how about y equals sine of the square root of x tangent x plus 3x. You can do the first one, you've got a basic understanding of chain rule. Second one, you're starting to get a little more involved. Third one, I think you're probably there. So let's take like 10 minutes and see how far you get, all right? And you can talk to each other. You're not turning this in, all right? Just raise your hand if you have a question. If you get the first one, raise your hand. I'm going to come by and check it. Yeah, that looks good. Yeah. The first one. Which one? This one?
Derivative of secant x, or tangent x, double check it. Derivative of tangent's not what you put.
That's a derivative of secant.
Did you raise your hand?
Yes.
Okay, right there. Yep. Yep. Yes. Mm-hmm. Okay, sorry, you're good. Which one is it? Oh, there we go, yep. Oh, just don't forget your x.
Can you check my last one?
Cosine of that, and then you have 1/2 that. How'd you do this one? So when you took derivative, you did product, right?
Yeah.
So is this your product right here?
That's the g, but this one, when you take the derivative
one.
of f, is 1, so I just put that.
Uh-huh.
And then I put the x up here, and then the derivative of that is secant squared x plus 3. Or no.
That'll work, but did you look at the product as happening between like
X and tangent.
x and just tangent and this?
It was basically this.
Because that matters. No. Okay, so you can't look at it that way. Because if you asked you to multiply this out, the product is happening between these two only.
Okay.
Right? So what you're going to do when you take derivative of this, do your product rule on these, right? Which would be, like you just did, 1 times that,
minus the 3.
plus this, right?
Not the 3 though.
The 3 will come out at the end.
Oh, okay, yeah.
Now, it turns out, in this problem, it does turn out that it looks like this would give you the same result,
Yeah.
but you got lucky.
But
If
if
this
this
would have
was
been
like-
something else,
yeah.
it would have been off.
Like an x
Okay?
squared or something.
Yeah.
Okay? All right, who else has the first one? Okay, your first one's good. First one looks good. No? So you need help?
No, I'm good.
You're good?
Yeah.
Okay. First one?
Then I'll work on the other ones.
Okay. Yep, first one's good.
All right. Sorry, just.
It's all right, you jumped right into the fire here today.
Yeah.
You got the first one? Okay, that's right. First one's right. So were you able to get through the product and quotient rule or no?
No, I'm not.
Not? Okay. So you're
Some
gonna,
of them on 2.2.
yeah, you're gonna have to get to that. I mean, it's gonna be hard to do this without that. So I think for today, just kind of try and soak in, but we're using rules you haven't seen yet. The only rule I think you're really comfortable with right now is that power rule.
Yeah.
So this, we're using quotient and product and the chain. So
what's the shortcut for any one of these?
well, all of them, yeah, the shortcut is the chain rule. You have to know what you have to know that this is a composition. You have tangent inside of a square root, right?
Okay.
So what we do is we start with the outer one, which is the square root. And you have to know that the derivative of the square root of x is 1 over 2 root x.
Correct.
Okay? So that means the derivative of this is going to be 1 over 2. Go ahead and write it down here, y prime. Root's on the bottom. Root of whatever's in here,
Tangent
x.
x.
Now you say times, and what we've done is we've taken care of the root, okay? Now we have to take derivative of tangent x, okay, which is secant squared x, so you just put it out there. So that's another thing you haven't,
So you flip the tangent to secant x. Is that what I'm saying?
no. You have, the derivative of tangent x is a formula that we derived already, that the derivative, just like there's not a rule for it, you just have to memorize it.
Oh.
Like the derivative of sine of x is cosine x.
Okay.
Derivative of cosine x is negative sine x.
Okay.
Derivative of tangent x is secant squared x. So those are things we just have to memorize. So you still have some catching up to do. That's why I was said if you come into this class, we're a little bit ahead of where you are. So it's going to be a catch-up game.
Sure.
Yeah. Okay.
Working on it.
Yes.
For the last one, do you do the 3 separately? Or
That's a good question. This is exactly the way you do it. It's because the product is only happening here, right? So when you go to take derivative of this, you see that it's 2 terms, right? So you're going to do them individually. So you're going to do the product rule here, right? And then plus the derivative of this. Now the only issue I see with this is that this multiplication has to take place. It has to impact the entire. So you need an additional parentheses here.
Wait, so 3
That's
is going to distribute?
Uh-huh.
Is it going to distribute in here?
No.
Or is it going to be
No.
plus 3?
It'll just be plus 3.
And this is wrong?
Nope, this is right. But you need this parentheses. You have to have that parentheses there. Because it's all of this multiplied times all of that, including the 3.
So if it was like if we were comparing it to the back of the book, we need like all of this on top of it.
Yeah, you would do all of that up on top. Yeah.
Oh, sorry. And for this problem, can you slide root sine x here and cancel the roots? It's like the problem we did earlier.
You know what? This was. Oh no, because this is not multiplication.
Okay.
See, if that was multiplication, you could cancel. But it's sine of that. So it's trapped in the sign and you can't cancel it. Okay? How are you doing over here? You understand the first one?
A little bit. I'm not sure if I got that right.
What's that?
I'm not sure if I got that right.
Yeah, that's right.
That's right?
Yep, that's right. So the second one, the only difference is that this is the same, except it's got an X in there. And then you're doing product rule on this, right? Good. So how are you doing the product rule? Let me see. So make sure you put tangent X here. Don't just put tan.
Oh, I thought it was like this is the this is the.
Yeah, that's right. I'm just saying you left the X off.
Oh,
You can't
okay.
just write tan. It has to be tangent of something.
Oh, okay.
Okay, so this is like your F and G kind of, right? And so you're doing derivative of this times this plus derivative of this times this. So just put your X there. That's it. That's perfect. That is what goes in here.
Yeah.
Okay?
And
And
this would be, has to
then,
be
yeah, where did
subscribed.
this one come from?
No, the yeah.
Yeah, okay, so that one's out. And that's it. It's all of this, right, on top of that. Yeah, you're there. I'm going to put the answers up here. And then I'm going to talk about number 3, or the third one here. All right, so that's the answer to the first one. A majority of you got that one without any issues. This one, the main difference is that you have a product rule happening inside. So you first still do the derivative of the root of something, which is 1 over 2 roots of whatever was in there. But then times Now, the inside, you have to do the product rule. And this needs to be in parentheses. So the product rule here is going to be the derivative of this times this plus the derivative of this times this. So derivative of this one is 1 times that, so just tangent x, plus derivative of tangent x, which is secant squared x, times x. So I'm going to put the x in front. That would be the answer here. Again, you have to have the parentheses, and then you could put this whole thing on top over here if you wanted to. This one, you have an additional element that there's a sign in front of all of the root, so you have to start with that. So we start this derivative. You have to take derivative of sine of something, which is cosine of that whole entire ugly thing. Okay, so that takes care of the outer function cosine. Now I say times the square root part. Derivative of that is 1 over 2 square roots of x tan x plus 3x. So I still have not taken derivative of what's in here. So now I'm done with the root part. So I move in, and what I notice on the inside, and this is the important thing here, I have 2 terms, don't I? Separated by addition. So the rule is that when you're taking derivative of 2 things that are to be added together, you do them individually. Okay? So I'm going to need to take derivative of this plus the derivative of that. And that's going to be multiplied here, right? So I'm out of room. I'm going to come down here. So I'm going to put myself a big old parentheses here. And I'm going to just remember, I'm going to have derivative of this plus the derivative of the 3x. I'm writing that down. You don't need that step, but that's what I'm about to put in here, okay? It's derivative of this plus derivative of that separately. Make sense? And it's tacked onto that multiplication out here. Now, when I take the derivative of this, I have to use the product rule. So I take derivative of x tan x, don't I? Which I already did. I did that back here in this problem, didn't I? And so the derivative of x tan x is this. And then plus the derivative of 3x, which is just 3. All right, so this is what I'll have. I'm going to erase these. This will be tan x plus x secant squared x plus 3. Parentheses have to be like this. You cannot close it off here, okay? And you can't not have the parentheses because it's all of this junk, right? Times whatever this is, and if it's 2 terms, that stuff would have to pass through to both. So you need those parentheses. Parentheses are one of the big things on tests that people forget or don't use properly that cost them points. All right, questions? I have given tests in the past. I don't know if I'll do it on this one. I have actually given tests in the past where, like problem number 1, I'll give an A level problem, B level problem, C level problem, and you choose. You can't do them all. You just have to choose one. And so if you do all the A level problems and you do them correctly, you can actually achieve an A on the test. But if you do all the C level problems, the highest you can get is like a 75. But they're easier problems, right? So I don't know if I'll do that again, but I've done that in the past. I've tried everything, man. I've tried everything. All right, well, here's what I would encourage you to do at this point. Since you've already done all the chain rule homework that I assigned, I would now go through and try and work the problems around the ones that I gave you. I mean, in my opinion, you should try and do every single problem in this section, page 121. You should try and do problems 1 through 42. I mean, you should, 42 chain rule problems is that's a good exercise set. That's going to take a while, but chain rule is one of those ones, I mean, it's just really hard to move forward in calculus at all without really understanding the chain rule. All right? All right, we're going to move on to a new section. Let me get my notes up here. It's chapter 2 still. We've done, so here's what we've done, right? We started out with the whole idea of the derivative. We looked at the derivative as a function. Then I gave you the basic formulas. That's where you learn the power rule. That's where you learn sine, derivative sine, cosine, tangent. All those are in 2.3. 2.4 is the quotient product rules. Now we've moved chain rule, and now we have 2 more sections. This is probably the hardest section in the entire class. Okay? In Cal 1, if you ask Cal 1 students what's the hardest thing, it's going to be related rates, and it's going to be optimization problems. They're both word problem sections, and they cause the biggest issues. All right? Just, I'm giving you some heads up. All right. Implicit differentiation. Implicit differentiation is something you have to know how to do and understand what's going on in order to do 2.7. So it's like we're going to learn something here, and then we're going to use it in word problems. So if you can't get this, it can make the word problems even worse, because then you don't have the math to do it on top of trying to translate the word problem into math. So this 2.6 is really important. So let's talk about 2.6. And I know you can read, but I have some typos in here, obviously. So fair, I think I meant so far. So far, we have been studying the derivative of a function of the form y equals f of x. That is, we have been looking at equations where we have y isolated on one side of the equation and the other side contains x in some way, like y equals sine x, or like the 3 problems I just gave you, it was y equals something, x was on the other side, but y was isolated. These are referred to as explicit equations, meaning we can express one variable, usually the y, explicitly in terms of the other variable, which is usually x. So we can actually determine exactly what y is if somebody gives us an x. Give me an x, I will provide you the y. All of our functions y equals f of x are explicit equations. That's what we call them. Some equations are very difficult to write in an explicit form. When we attempt to get them in an explicit form, we run into difficult algebra, and sometimes we obtain multiple equations. What? I think I meant to say these are implicit equations. Here are some examples. Okay, explicit equations. Y equals 3x plus 1. That's a line. Standard old college algebra, that's explicit. We can solve for y. Y equals square root of sine x. Explicit equation. We can solve it for y. This one right here, explicit equation. Now it's not solved for y, but it's solved for x, isn't it? We can get x in terms of y. You give me y, I give you x, right? This is an explicit equation. So it doesn't have to be y that gets isolated. It can be any single variable. So if you can isolate a single variable, we call it an explicit equation. Here are examples of some implicit equations. Let's take a look at that first one. Could you isolate y? If I asked you to try and get y by itself right here, you could do, how about this? Subtract x squared from both sides. So you almost have y by itself, but that's y squared by itself. So you'd want to try and get just y, so what would you do to get rid of the square? Take the square root. But there's a problem with that. What happens if you initiate a square root on both sides of an equation? You have to do plus or minus. Okay? And so what winds up happening is that you get y, but it's not explicit because there's actually 2 definitions of y. There's a positive case and a negative case. So this is not explicit. If I give you an x, are you going to give me a y? No, you're going to give me 2 y's, and that's not explicit. That's what we call implicit. Understand the difference? Okay. Now, does anyone know what this looks like? Where are my pre-cal people? Y'all had me last semester. Y'all, please save me. That's a circle. Good. That's a circle of radius 4. That's a circle of radius 4, isn't it? Okay. If that's a circle of radius 4, it's also centered at the origin. All right? Because of the format, if you remember, this is the standard format of a circle. That's your general equation of a circle centered at HK radius R, pre-cal. So that is our circle equation. Who cares? That's a circle radius 4. What is different about this picture compared to the others that were up here? I'll give you a hint. It doesn't pass the vertical line test. This is not a function of x, right? It fails the vertical line test, which is the test that we run for functions, right? If I draw vertical lines and I hit it more than one time, like here I'm going to hit it twice, I would hit it twice. If that happens, then we say this isn't a function, right? But it has tangent lines. I mean, come on, right? Like, look, if I pick a point, there's a tangent line there, right? If I pick a point over here, there's a tangent line. Pick a point right here, there's a tangent line, right? So this graph has tangent lines. The question is, can we actually find them? Just like what we were doing before in the previous sections is we had functions, didn't we? And we were finding slopes of tangent lines, weren't we? What we're doing in this section is saying, what if we have something that's not a function of x, that looks more like this, where it fails to be a function? Can you still get tangent lines? The answer is yes, but we have to introduce a new type of differentiation, and it's called implicit differentiation. All right? That's what it's called, implicit differentiation. I'm pretty sure everything I just put up there is about to be drawn out for you here. Yes. But there's something in this little illustration that I think might be helpful. So that's that circle, right? So I have a tangent line there, right? Goes around. But if you look at the x-coordinate here, whatever that x-coordinate is, there's actually two different y values for that x-coordinate, right? And remember, when we try and solve it for y, we got this equation. So if you give me an x, it spits out the two y's. You give me an x, it spits out that y and that y, the positive and the negative, right? So there's actually two tangent lines. So if I provide you an x, that's not enough information for you to tell whether or not it's going to be this point or this point. Do you all see that? So with implicit equations, these non-function things, having x provided is not enough. We're actually going to have the x and the y provided. I have to tell you, it's this x, that y, I want that tangent line. Or I give you this x and this y, which would be a different y, and then you would get that tangent line. So somehow in the formula, when we take the derivative, our answer is going to need to have x's and y's in it, which is weird. You'll see, as we move through this, hopefully that'll become a little clearer for you. All right, I gave you three examples, right? Here's one right here. You cannot solve that for y. All right, there's no way to get y by itself. And you can't get x by itself either. All right, just not going to happen. But if we graph it, that's what it looks like. There are points, there are x's and y's that you could plug into that equation that would create a true equation, and these are all the points that do it. That obviously fails the vertical line test. Not only does it fail the vertical line test, right, it fails the horizontal line test. I mean, this is not a function, but it has tangent lines. I mean, they're there, right? Just don't worry about that little jag. That's the computer freaking out, okay? All right, so I've got tangent lines as I move things around here. Again, for the same x value, I have two different y values, but two different tangent lines, right? So somehow we're going to need to be able to recover these. Let's move to the other side. Over here, same x value, two different y values. So again, the derivative is going to need us to somehow feed it the x and the y to give us an answer. So you'll notice that when we take the derivatives in this section, our answer, you know how like we've had like y equals x squared, the derivative of this was 2x. Notice that to find the slope of tangent line, all you have to give me is x, right? Today, like in this stuff, our answer over here is going to have x's and y's in it. That will allow us to actually isolate which point it is. All right, let's take a look at this. I didn't do the last one? I didn't. Okay. So here it is. As we can see above, the curves are not true functions, blah, 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 multiple outputs, blah, blah, blah. We need to study a new form of differentiation called implicit differentiation. I will do numerous examples in class. All right, here we go. That's it for the notes. Implicit differentiation. All right, so first example. Let's go ahead and knock out that circle, because the circle is the easiest one to look at and kind of visualize. All right, so there's an equation, right? That draws a circle, radius 4. I would like for us to find dy dx, which really means y prime, doesn't it? Now, to do this implicit differentiation, I have to start really stressing to you a couple of things that I didn't have to stress before. When you write dy dx, we are saying that x is the independent variable. And we are saying that y is the dependent variable. Meaning, somebody is going to give you an x, and then y will come from that, right? So y depends on what value of x is given. X is independent. It can just be whatever somebody wants it to be. Does that make sense? The difference between dependent and independent. All right. So right now what we're going to do is stress one more thing. This means that y is, I'll just say, depends on x, just to make sure you really understand that. Depends on x. You could almost say, if you wanted to, that y is almost like a function of x, because it depends on what you give, what the x input is. All right. Here's how we do it. Here's the actual work. Solution. What you'll do is you'll start off by writing out the equation. And you're not going to try and solve for y. You're just going to leave the equation written exactly the way it's presented to you. And then what you're going to do is you're going to take the derivative of both sides of the equation at the same time. And you're going to take the derivative with respect to x. And what I mean by that is we are going to be treating x as the independent variable. So watch me on this first one. I'm going to take the derivative with respect to x. That's some notation we saw back when I was showing you all the different notations for derivatives. I'm going to take the derivative with respect to x of the left side, and then equals the derivative with respect to x of the right side. So it's kind of like the way we work with the equations. You do something to one side, you have to do the same thing to the other. That's what I'm doing here. I'm taking derivative of the left side, derivative of the right side, and I'm going to see what happens. Let's do the right side, because I think the right side's easier. Do you know what the derivative is with respect to x of the constant 16? 0, right? Because 16 is a constant. All right. So the right side's 0. That's good. All right. Now I'm going to be taking the derivative of this, right? This is the part that's tricky. All right? For this first one, let me write it this way. We're going to be taking the derivative with respect to x of x squared plus the derivative with respect to x of y squared. So all I'm doing is I'm taking derivative of each of these separately. I can do that because there's addition, right? So I'm just going to do them individually. Now, what is the derivative of x squared with respect to x?
2x.
Should just be 2x, right? Does that make sense that it would be that? Okay. That is what it is. So the derivative of this is going to be 2x. What is the derivative of this? What is your gut telling you? 2y? It's almost 2y, but it's not 2y. Not exactly. I need to explain it though, right? So I'm going to try